Good morning. We will start today's lecture with a review of the MOSFET and the BJT. So this is the MOSFET. With the MOSFET gate, the gate terminal, the MOSFET source, and the MOSFET drain. We have two voltages that enter in the equations of the MOSFET current, the VGS, the MOSFET gate to source voltage, and VDS, the MOSFET drain to source voltage, so VGS and VDS. And we have only one current in the MOSFET, ID, flowing from the drain towards the source. This is when the MOSFET is N-type or N-channel, and it flows in the opposite direction for P-channel when the arrow points like this in this direction. So in the first part of the course, we will study analog electronics and amplifiers, as we said last week. And to amplify, the MOSFET should be operating in the saturation region, because this is where we can obtain amplification. In the saturation region for N MOSFETs, N-channel MOSFETs, VGS and VDS have to satisfy certain conditions. VGS should be greater than the threshold voltage of the transistor, VT, and VDS should be greater than VGS minus VT, this quantity we call the overdrive voltage. So VGS and VDS should be large. VGS larger than the threshold VT, and VDS larger than the overdrive VOV, which is equal to VGS minus VT. If this is a P-channel MOSFET, then we consider the absolute values. So the absolute value of VGS should be greater than the absolute value of VT, and the absolute value of VDS should be greater than the absolute value of VGS minus the absolute value of VT, because VGS, VDS, and VT are negative in the case of the P-channel MOSFETs that we studied. This is the BJT, the bipolar junction transistor, with its base terminal here, collector, emitter. So B, C, E, and we're showing here all the voltages, VBE between base and emitter, VCE between collector and emitter, and VBC between base and collector. And we have also three currents, IB, the base current, IC, the collector current, and IE, the emitter current, which is IB plus IC. So again, for amplification, we bias the BJT in its active mode or active region. The symbol here is showing an NPN BJT, and for NPN BJT in the active mode, again, VBE and VCE should satisfy certain conditions. They should be large, and VBE should be larger than VBE on. which is around 0.5 volt, and VCE should be greater than VCE edge of saturation, which is that 0.3 volt value we used to check. So VBE greater than around 0.5 volt for silicon NPN BJT, and VCE greater than 0.3 volt for silicon NPN BJT. And again, if this is a PNP, VBE and VCE would be negative. So we can use the same conditions with absolute values. Absolute value of VBE should be greater than 0.5, and absolute value of VCE should be greater than 0.3 volt for PNP. And in the PNP, the arrow would be pointing like this from the emitter towards the base. The current voltage characteristics, the current equations for the MOSFET in SAT, and again, we're only considering the SAT region, just one region, because we will focus on amplifiers. So the MOSFET in SAT would have such current equations. IG is zero. IG is zero. That's always, pretty much always. There's no gate current. There's only one drain current in the MOSFET. And the drain current is given by half mu NC oxide W over L VGS minus VT squared. And if there is what's called channel length modulation, then ID will also depend on the value of VDS, and we multiply the expression by 1 plus VDS over VA. So this is a correction factor to model the channel length modulation. In other words, to model that ID does not only depend on VGS in SAT, but it may also depend on VDS. And we used K prime instead of mu n C ox. So K prime is really just mu n times C ox, the mobility times the oxide capacitance per unit area. So in the equation, it may be half K prime W over L, or sometimes we used half K, and K would be K prime times W over L. And VA in this channel length modulation correction factor is also dependent on L. So if I increase L, VA would increase. So this equation VA equals VA prime times L shows that if I change the dimensions of the MOSFET, the value of VA for the MOSFET would change. For the BJT in the active region, the collector current IC is given by IS e to the VBE over VT, and the base current is the same quantity divided by beta. So IC is beta IB in the active region, but also IC is IS e to the VBE over VT. If I have early effect in the BJT, then the expression of IC, this IS e to the VBE over VT, would be multiplied by 1 plus VCE over VA, where VA is called the early voltage. And this correction factor models the fact that IC may also depend on VCE in active, not just on VBE. So there may be an increase of IC when VCE increases in the active region. So this is the summary of the current equations in the regions where the transistors can be used as amplifiers. Now, in the case of amplifiers, a very useful technique is the small signal analysis, where we can use the small signal equivalent models of the transistors. What these do, what the small signal equivalent models allow us to do, is get rid of non-linearities. So there's no power, there's no square term in the MOSFET, or there's no exponential in the BGT. We can linearize the equations and everything becomes just linear. And the reason we can do that is because the signals are small. So when the signals are small, we can approximate the nonlinear functions by just its by the linear expression, linear expansion. And if we do that, then the model of the MOSFET, as far as signals are concerned when they are small, so that's the small signal model, would be just this control source, a voltage controlled current source. So there is a GM VGS, and that's as you can see, a linear expression. GM times VGS, no square, no exponential, no cubic terms. So GM times VGS, and this will be the current flowing in this control source. And if there is no VA or lambda, we also used lambda, which is just 1 over VA. If there's no VA or lambda, then that's it. This would be it. And if there is, then the model is augmented by a resistor, small RO, between drain and source. So that goes in parallel with this GM VGS in the case of this so-called hybrid pi model. For the BJT, the hybrid pi model, including the small RO, would look like this. So similar to the MOSFET, with the exception that in the case of the BJT, I have a resistor here between the base and the emitter, while in the case of the MOSFET, there is an open circuit. So this resistor in the case of the BJT is not infinite, it's finite, it's called R pi, and it models the fact that there is base current in the MOSFET, all right? There's this IB here, and while there's no IG in the case of the MOSFET. So IG is 0, is reflected in an open circuit, while there is some IB, and that's reflected that there is a resistor that would allow an IB to flow. So these are called the hybrid pi small signal models of the MOSFET on the left and the BJT on the right. And the values for GM and RO are given by these expressions. In the case of the MOSFET, GM is ID over half VOV, and VOV is VGS minus VT. And note that the ID and VOV values are the DC values of the drain current and the overdrive voltage. RO is given by VA plus VDS divided by ID. And this is equal to VA over half K or K prime W over L times VOV squared. So these are the expressions for GM and RO. Similar expressions for the BJT. GM is IC over VT. So the DC value of IC divided by VT, and VT is not the threshold voltage of the MOSFET. Don't confuse VT with a capital T with VT with a small t. V sub small t is threshold voltage of the MOSFET. V sub capital T is the thermal voltage. This is a quantity that just depends on temperature. Depending on the temperature, we have a certain VT, and you may recall that its default value is around 25 millivolt. That's the value of VT at room temperature. RO is VA plus VCE over IC, and that's also equal to VA over ISE to the VBE over VT. And we have the additional R pi for the BJT, and it's equal to beta over GM. So the product R pi times GM is equal to beta. Beta is this IC over IB in the active region. And for completeness, we will also review the small signal T model. The small signal T models are another way, another set of models for the transistors, and they give the same results, of course, if we use the small signal T model or the small signal hybrid pi models. So this is on the left, the small signal T model for the MOSFET, and on the right, the small signal T model for the BJT. And we have this resistor, small resistor, which is 1 over GM in the case of the MOSFET, or alpha over GM in the case of BJT. Alpha is beta over beta plus 1, and it's a number that's very close to 1. And there is this current here. This is the current flowing in RE, and the current flowing here, alpha IE. The difference between them, this current minus this current would be the base current. While here, in the case of the MOSFET, this current minus this current would be exactly 0, because there's no IG, even though there's like a wire here, but there's no current that's flowing there. So this current is exactly equal to this current to make IG 0. While here in the BJT, this current minus this current, there is something, and this something would be the base current of the BJT. Let's introduce a quantity, just a simple quantity called intrinsic gain. It's like how much gain I can get out of the transistor. So for the MOSFET, I will assume that I have a MOSFET and I have some signal at the gate. So of course, the MOSFET is not just operating by itself in a vacuum. It has to be part of a circuit, and it has to be biased in the saturation region. So the DC VGS is greater than VT, the DC VDS is greater than VGS minus VT. So properly biased, and there is a signal somehow that appears between a gate and source, a small VGS that appears there. I want to see what would appear at the drain. So I want the gain from gate to drain. So if there is a small VGS that appears between gate and source, a small signal, what happens at the drain? Well, I want to find the voltage here as divided by the voltage here. And I will take the source as my reference. So what would be VDS over VGS? We call this the intrinsic gain or the internal gain. Well, if this is the situation, this is my circuit, then this current would be circulating here. And the current NRO would therefore be flowing up and equal to GM-VGS. So VDS with a plus here and a minus here would be minus GM-VGS times RO. So we see this here, minus GM-VGS times RO, divided by VGS, which is our input in this case. And this means that the intrinsic gain is minus GMRO. If we do the same for the BJT, that's the small signal model. And again, this is for a BJT that's properly biased in the active region, and there is a signal that appears between base and emitter, and I want to see what do we get here at the collector or between collector and emitter. Again, if this is the whole circuit I'm analyzing, then this current would circulate like this. And again, VCE would be minus GMV pi times RO. And the input is the voltage V pi between base and emitter. So again, the intrinsic gain would be minus GM RO. So same expression for MOSFET and BJT, their intrinsic gains have the same expression, minus GM times RO. So minus means that there is a signal inversion between the gate and the drain for MOSFET, and between the base and the collector for BJT. So if at the gate I have a sine omega t millivolt, at the drain I may have minus 50 sine omega t millivolt. So it's also a sine wave, but it's inverted. Same for the BJT. There is also inversion between base and collector. Now let's see how much is this GMRO. This is intrinsic gain. So this is like how much gain we can hope for from a transistor. And this should be a large number. If we say that the transistor is a good amplifier, then this intrinsic gain should be a large number. So let's take an example to see. Let's consider a MOSFET and a BJT. Both are biased at 0.1 milliamp. So the MOSFET drain current is 0.1 milliamp, and the BJT collector current is also 0.1 milliamp. And then we'll take some kind of typical values for a MOSFET. VA prime is 5 volt per micrometer, W is 4 micrometer, L is 0.4 micrometer, and K prime, which is mu C oxide, is 267 microamp per volt squared. Notice the micrometer dimensions. We remember that this is a course about microelectronics, so all the devices are very, very small. The BJT is also biased at 0.1 milliampere in the collector, so 0.1 milliamp. VA is 35 volt, VT is its default value at 25 millivolt, and beta is 100. So what would be, in this case, RO, GM, and A0? I want to know the value of the small signal parameters and the intrinsic gain. So to get RO, I need VA and VOV, or VA and VDS and ID. So I have ID, I have VA. VA is VA prime times L, so I know VA. But I don't know VDS. So something that we usually do is we neglect the VA effect in DC analysis. And this may seem like a contradiction, but it doesn't cause a lot of error. So where's the contradiction here? We neglect VA in the DC analysis, but we use small RO in the small signal analysis. So it's like saying there is channel length modulation only in signals, but there's no channel length modulation for DC. We do this to simplify the analysis, and the error that is caused by this is usually acceptable. So we neglect VA in the DC analysis, and if we do that, then the current equation in the saturation region for the MOSFET would be ID is half K prime W over L VOV squared. K prime is mu N C oxide, and I have the value of that. I have W, I have L. I know ID, then I can find VOV, and it will be 0.27 volt. So now I have VOV. I can find RO, VA prime times L, that's VA. RO is VA over half K VOV squared. So half K is half mu NC oxide W over L VOV squared. I have all these values now, and I can find RO, it is 20K. So that's RO. GM is ID over half VOV. ID is 0.1 milli, VOV is 0.27 volt, and I get 0.73 milliamp per volt. Okay, so these are typical values for a MOSFET, like an RO in the tens of kilo ohms and a GM around 1 milliamp in the range of maybe fraction or a few milliamps. Typical values. What about the BJT? The BJT, oh yeah, before we go to the BJT, we get A0 in this case, minus GM RO. So minus 0.73 times 20 minus 14.6 volt per volt. Intrinsic gain has no units, but we write volt per volt. For the BJT, RO is VA over IS e to the VBE over VT. Again, we neglect VA, the early effect in the DC analysis. So RO is approximately VA over IC, and that's 350K. VA in this case is 35 volt. GM is IC over VT, 0.1 over 25, so 4 milliamp per volt. What is the intrinsic gain in this case? Minus GMRO is minus 1,400, 1,400 volt per volt. So we see here something interesting. The BJT has much higher intrinsic gain than the MOSFET, almost 2 orders of magnitude higher. And to understand the reason why, we have actually two components in the A0 equation. It's a product of GM and RO. If you look at the GM of the BJT, it's 4. If you look at the GM of the MOSFET, it's 0.7 to 3. So GM of the BJT is greater, like 5 times maybe bigger than GM of the MOSFET. And that's because GM of the BJT is IC over VT, and this is 0.025 volt, while GM of the MOSFET is ID over half V of V, and that's maybe 0.135 volt. The other thing is that RO of the BJT is 350 kilo ohm, while RO of the MOSFET is just 20 kilo ohm. So RO is much bigger in the case of the BJT. Can we do something about this? Can we make the MOSFET, can we get more gain out of the MOSFET? Well, what is the expression of RO? Maybe we can increase RO. It's VA here, and VA is quite small. VA is VA prime times L. So can we increase it? Now, one thing about MOSFETs is that W and L are dimensions that we can control. So W and L for electrical and computer engineers are 2 parameters that we can set. When we design a circuit, we can determine and set W and L. So maybe we can make L bigger. And if I make L bigger, then this will be bigger. What about this? L also appears here. So I will disrupt VOV, and that may affect GM. So maybe I can make W also bigger. If I scale W and L by the same factor, then VOV is not affected, but RO will increase and GM will be the same. So if I make W and L much bigger than what they are, for example, 50 and 5, instead of 4 and 0.4, and I repeat the calculation, I will get an intrinsic gain for the MOSFET, which is almost minus 200, minus 183 instead of minus 14.6. So I can make the gain bigger. But what is at what price? What is this new MOSFET that I got? It's a 50 by 5. Its width is 50, its length is 5, while the original one was 4 by 0.4. So this was if I take the product W times L as the area of the MOSFET, this was 4 times 0.4, so 1.6 micrometer squared. This one is 250. So this is a much bigger MOSFET. The area is much bigger. So this is the price that I pay. I can get more gain, but then I have to use a larger MOSFET. But if I use a larger MOSFET, the gain would be quite reasonable. Still, the BJT may give me more gain. So if I am after just large gain and I have the option of choosing MOSFET or BJT, then the BJT looks very good. But of course, there are other things to consider, and the MOSFET is also a very competitive device in analog and digital electronics, of course. Any questions before we continue? A question about the size of the BJT, and as you can see, the expression for the BJT has an IS in it, and IS actually depends on size. And you can make the BJT larger or smaller by making the emitter area large or small, and that will affect the value of IS. Yes, of course, we can control the BJT, but already its intrinsic gain is 1400. So we can make it bigger, but it's winning anyway now. Any other questions? Does the size affect VOV? Well, if I scale W and L by the same factor, if I make W 10 times bigger and L 10 times bigger, and ID is 0.1 milli, then if you look at the equation, ID is half K VOV squared, and K is not affected because W and L were scaled by the same factor. So K is the same, ID is the same, VOV will stay the same. So if I scale W and L by the same factor, VOV is not affected. If I only scale L, then of course VOV will be affected. Or if I only scale W. But if I scale L and W by the same factor, then VOV will be 0.27 volt. Okay, let's start now with our first new circuit. We want to build the current source now. So here's the basic MOSFET current source using NMOS transistor, N-channel MOSFETs. Two MOSFETs, Q1 and Q2. Their gates are connected together. Their sources are connected together. And in this case, the sources are grounded. And because the gates are connected and the sources are connected, VGS will be the same for Q1 and Q2 because the gates are together and the sources are together. They will have the same VGS. For Q1, there's a connection between gate and drain. So the drain of Q1 and the gate of Q1 are shorted together. So the voltage here is the same as the voltage here. So the voltage at the drain of Q1 is equal to the voltage at the gate. And this means that VDS of Q1 is the same as VGS for Q1. And then I have a resistor from the drain of Q1 to the supply VDD. This resistor is R. And the current that I call the reference current is flowing in R. And I'm showing here ID1. And this is the transistor ID2. And I consider this to be my output current. And here the node is the output. So this will be the voltage at the output node. I don't want to call it the output voltage because I'm building a current source. So there's an output current and there is a voltage at the output node. So this voltage here, we call it VO. This current is my output current. This is the quantity of interest. I want to see how much would this IO be. And this is the circuit structure. Two transistors, one of them with gate connected to drain, shorted to drain, and the other with drain connected to something else that we're not showing. But I want to know what IO is. And remember, we're building a current source. So if IO is the output current, it should be a constant current because I'm building a current source. So Q1 has VDS equal to VGS. Now it's an N MOSFET, so its VT is positive. So VDS would be greater than VDS minus VT, right? If VDS is positive and VT is positive, then VDS would be greater than VDS minus VT. Like 5 would be greater than 4 if VT is 1. But what did we say about VDS? VDS is equal to VGS. So I will replace this VDS by VGS. And if I replace it, then because of this short between the drain and the gate, VDS would always be greater than VGS minus VT for Q1. So if Q1 is conducting current, then it's in SAT. Of course, there's the additional condition that VGS should be greater than VT. So assuming that it's conducting current, because if it's not conducting current, then the circuit would be trivial, would be useless. We need current to flow in the circuit for the circuit to be useful. So assuming that current is flowing, if current is flowing, then Q1 is definitely SAT. The other option would be triode, but it cannot be in triode because of this short circuit. VDS is equal to VGS implies VDS greater than VGS minus VT. So Q1 is SAT whenever it conducts. Whenever the circuit is used as a current source, it should have some current in it. And in this case, Q1 will be saturated. So we can use the equation of ID1 and SAT. ID1 will be half K prime W over L1, VGS minus VTN squared. So this is ID1. Now, what is IRF? Let's see, what is IRF would be ID1 plus this current. What is this current? This current is flowing down. It will be this current plus this current. But what are these currents? These are gate currents of MOSFETs. So this is 0. This is the gate current. And this is also 0 because it's the gate current of Q1. So the two gate currents are 0. Their sum will be 0. So this is 0. So what does this mean? It means that this current is equal to ID1 because there's nothing flowing like this, even though I have a short here, but there's no current flowing in this short. So ID1 will be equal to IRF. And what is IRF? It's the current flowing in the resistor, VDD minus the voltage here over R. So that's ID1, and that's IRF. Okay, so these equations give me what's happening on this side of the circuit. And notice that this side of the circuit determines ID1, which is equal to IRF, and also determines VGS. Because if I solve these two equations, I will know what is ID1, what is IRF, and what is VGS. Of course, I would need to know the transistor dimensions and the value of VT and the value of the supply voltage and so on. But what's important is that this part of the circuit determines everything here and also VGS, and is not really affected by the presence of Q2. The fact there is a Q2 connected here did not enter in these two equations. All right, so Q1 and R and VDD determine VGS. Okay. What about Q2? What happens there? Now Q2 will be SAT when the voltage at the output node is greater than VOV. The reason is that the voltage here is equal to VDS2. So when VDS2 is greater than VGS minus VT, and I'm not saying VGS2 minus VT because VGS2 and VGS1 are equal and they're both just VGS. When VDS2, which is VO, is greater than VOV, VGS minus VT, Q2 will be SAT. So We cannot say for sure that Q2 is SAT because there's no short circuit between gate and source, between gate and drain for Q2 like Q1. There's no short here. So I'm not sure. Maybe this voltage is large, maybe it's small. If it's large, larger than VOV, then Q2 will be SAT. If this is the case, then ID2 will be half K prime W over L2 VGS minus VTN squared. And this will be the output current here, IO, flowing in the drain of Q2, assuming that nothing else is connected here. So this current continues to flow in the drain of Q2. So IO is therefore half K prime W over L2 VGS minus VT squared. And now, if I use MOSFETs that are matched in their K prime and VT, if they have the same K prime and VT, and I take the ratio ID2 over ID1, I will get IO over IREF. IO is ID2 and IREF is ID1, equal to W over L2 divided by W over L1. Okay, so IO over IREF is W over L2 divided by W over L1. Now, this is a very interesting formula. Why is that? IREF is determined by this part of the circuit. Whether Q2 is connected, whether Q2 is disconnected, irrespective of Q2. So IREF is determined by this part of the circuit. So once it's determined, then whatever happens here, IREF will not change. So IREF is therefore a fixed current. W2, L2, W1, L1, these are dimensions. These are fixed dimensions. They will not change when voltages change or current change. These are just dimensions, physical dimensions. They have width and length. So they're fixed. So if this is fixed, and this is fixed, what does this make IO? It makes IO a fixed current. So irrespective of what happens here at this node, IO is a fixed current. And that makes this the equation of a current source. Because what is the current source? It's a device that will give me a fixed current irrespective of the voltage across its terminals. So irrespective of the voltage here, this current is always the same. Of course, Q2 should be SAT, but this is a simple condition. And VO should be larger than VOV, 0.2, 0.3, 0.5 volt. As long as VO is larger than maybe a fraction of a volt, the current here is fixed, will be the same. So this is the importance of this equation. We just built our first current source. IO is some fixed current determined by the left part of the circuit times the ratio of dimensions, and that's also a fixed quantity. So that's nice. But then, why is this really interesting? Okay, big deal. I have a current source. Let's look at some circuits from like real industrial designs. This is a circuit from the microwave journal about an amplifier. And if you look at the circuit, you see here, what do you see here? You see a current source. You see here another current source. So these are really used in actual circuits, and we need them to bias amplifiers. So how do you build them? When you see something like this circuit, and you have, well, of course, there are like resistors and MOSFETs and capacitors, and that's fine. But what about these? How do you build these? Now we know. Now we know that this is actually another circuit. This is like a sub-circuit that is built using what? Using MOSFETs also, using transistors and resistors. But we don't show them every time. We don't show all their details every time. We just show them as current sources. So these current sources, like this one here and this one here, they're built also using transistors and resistors. And the circuit we saw on the previous slide is just a very simple, basic current source built using N MOSFETs. So we will see that we need in many circuits such current sources. And now we know at least how to build the very simple basic one. All right, so here's our simple current source. And we said that the output current is a fixed current as long as the voltage at the output node is larger than VOV. And it's fixed because it's the ratio of dimensions times IRF, and IRF is fixed because it's determined by the left half of the circuit. Very good. What if I have channel length modulation? We neglected that, but what if we cannot neglect it? Now we have to rederive the expression with VDS1. VDS1 is VGS, and VDS2 is VO. So if I rederive the expressions, the expression for ID2 will be multiplied by 1 plus VDS2 over VA2, and ID2 is IO. And the expression of ID1 will be multiplied by 1 plus VDS1 over VA1, and VDS1 is VGS, and ID1 is IRF. So now IO over IRF is no longer this fixed ratio of dimensions. Now I have this also. This correction factor because I have channel length modulation. So is this good news or bad news? Well, let's see. VA1 and VA2 are fixed. They're, once the dimensions are set, the VA prime value is set. These are constants. One is a constant. VGS is determined by the left half of the circuit, so that's fixed. But this is really annoying. Now, because of VA, because of channel length modulation, the output current depends on the voltage at the output node. What does this mean? That means that my current source is no longer an ideal current source, is no longer a pure current source, because in an ideal current source, the output current IO should not depend on the voltage VO. But now, because of VA, the output current depends on VO. Fine, maybe it's not a big deal. Let's see. If I plot what happens in the circuit, say using SPICE, I simulate the circuit in SPICE and I plot IO versus VO. What I'm hoping for is that IO would be fixed, would not depend on VO, because I'm trying to build the current source. So what I'm hoping for is to get something like this, to get the blue line. Because why am I hoping to get the blue line? Because the blue line is a fixed level. And the blue line, if I translate it into a sentence, means that IO is fixed irrespective of VO. Am I getting that? The simulation shows me that I get this. Well, why am I getting this? Because these are the characteristics of the MOSFET, really. But if we restrict the range of VO to what we said, VO should be greater than VOV. Now, we should really not consider this part. Let's forget about this part because we said that VO should be greater than VOV. And then if we just compare the part here, the real blue curve, with the ideal thin blue curve or blue line, which should be horizontal, then they're not really that different. I mean, they're not the same, obviously, but they're not that different. And the slope of the line, of the ideal line, will be zero, while the slope of the real line is not zero. And we can show it's 1 over small r02. So the effect of VA is therefore to make the slope of the line non-zero. If it's ideal, if the current source is ideal, the slope of the line should be zero. I should get the horizontal line, but I don't get that. I get something that I get a line or something that looks like a line, like a straight line with a small slope. So that's fine too. And we will discuss later how we can measure how ideal or non-ideal or how close to ideal we are for such a current circuit, for such a current source circuit. Any questions? Please remember to join the WhatsApp group of the class. The link is on Moodle. Also check the Moodle page regularly for any announcements or material that I post there.